Okay, so let's get started. Here we go. If you got an NP, on the mastery the first time, and you didn't come Wednesday night, you got to make arrangements with me soon to take this soon. Okay? Because as long as you have an NP there, you have a 0. Okay, so you got to retake it. Let's see. I think I said that you would get 85% of your score on the second attempt if you passed it. So that's going to be 90% of your score on the second attempt. So if you get 100 on the second try, you got a 90 on the mastery. If you got 90 out of 100 on the second try, you got an 81% on the mastery. Someone said, wait, that's better than what I said. That's better. All right. So I want to review kind of, you've got a taste of these related rates problems, really important problems because they really force you to take this information in written form and assign quantities to it. So this is what it's about. And then assigning the right symbols to those quantities. So let's just review it again and practice. You're going to get... So we're going to have another round of those in web work, but they'll be more difficult. Okay, so you've got your feet wet with the easier ones. So what's our approach? What's the centerpiece? Okay, that was not a cue to start talking. Okay, so yes, those were the easier ones. So we got to do some harder ones. So the centerpiece of related rates. What is our centerpiece equation? If it's a related rates problem. Equation that relates rates, right? So it's the equation. So this is the first time in the semester we've seen more than one rate of change in the same situation. And that's the whole point. You have an equation that brings together more than one rate of change. And so that equation that brings together those rates is the centerpiece of the solution. And where does that come from? From differentiating what? An equation that relates those accumulating quantities for those rates that we're relating. Okay? So this is what we talked about last time. So we're going to get the related rates equation from the related accumulating quantities equation. So here's that strategy. First, read and identify and define symbols for all the rates that they're giving you. Okay? So maybe those are known values, or maybe you have to solve for one of those. But identify all the rates of change. And then put symbols on it. dx dt, dv dt, whatever, dy dt. Okay? And then from those rates, we want to identify and define symbols. You kind of already have done that for the accumulating quantities that are corresponding to those rates. All right? So if it's how fast the volume is changing is one of the ones at number 1, then we have a quantity of volume. So we want to identify that. Precisely use variables, okay? And so once we have those accumulating quantities defined, we want to set up B. We want to set up the equation that relates the accumulating quantities, and then we do our implicit differentiation with respect to T to get A. That's our goal. Our goal is A, the equation that relates the rates. Okay? And then we use that to solve for whatever unknown quantity that they are asking for. Okay, so this should feel very familiar now that you've worked that. If you didn't take quite this approach and you had struggled and had difficulty, then I suggest that you kind of learn what I'm emphasizing here, and maybe that will help you. Okay, so let's do one more. So I've got that same thing here on the left to kind of guide us through. And here's an example. So a street light is the top of a 16-foot pole. A woman 6 foot tall walks away from the pole. Her speed at 4 feet per second. How fast is the tip of her shadow moving along the ground when she is 35 feet from the base of the pole? So let's always start with a picture if you can. All right, so we'll start with a picture here. So it's a 16-foot light pole. Okay, and then here's the ground. And she's walking away. If you like my street light, you're going to really like my... Okay? And she's walking away at 4 feet per second. And so as the rays of light pass the top of her head, along that line is how is this going to project her, the tip of her shadow is going to project onto the ground. So then her shadow is something like this. Okay? So does the situation make sense? And she's walking away from the pole at 4 feet per second. Okay, so what are we going to do? We're going to figure out what rates are involved. What rates are involved? So what's the first rate that we come to here? It says the street light is the top of a 16-foot pole. She's 6 feet tall. She's walking away from the pole at a speed of 4 feet per second. There's our first rate. Okay, there's our first rate. So here's the thing about speeds, though. What type of quantity is that the rate for? So you can't just think of it as this woman and her focusing on her going 4 feet per second. There's a quantity that's changing at a rate of 4 feet per second. What kind of quantity is that? A distance quantity, right? So if you're just focused on the woman, you're never going to come up with the fact that this is a distance that's changing with respect to time. So in the picture, what distance is it that's changing at a rate of 4 feet per second? Distance, so it's this distance from the light pole, you see? So what do we want to call that? Doesn't matter, anything you want. Start with x. Okay, so this rate, 4 feet per second, how can we write it symbolically as the rate of change? dx dt. So we're given that dx dt is 4 feet per second. So when you have speeds, you got to take your focus off the object and figure out what distance is changing at that rate. What distance? And this is going to be especially careful. So now it says, how fast is the tip of her shadow moving? Okay, again, how fast the tip of her shadow? That is also going to be a distance. So if you just focus on the tip of her shadow, you'll never get that there's some distance that's changing at a rate that we're trying to find. So what distance is it? Is it this distance right here? Will the rate of change of that distance give us how fast the tip of her shadow is moving? Oh, some people are saying no. Okay, how about that distance? The rate of change of that distance would be how fast what is changing? If we took this distance right here, so let's call it, we'll call it y, just for now. If we took dy dt, would that be how fast the tip of her shadow is moving? And if not, what would it be instead? No, what would the dy dt mean in this situation? The rate of change of what? The length of her shadow. The rate of change of the length of her shadow. Why is that different than how fast the tip of her shadow is moving? Why is that different? Because this point is moving, you see? Because she's moving. The rate of change of y will not be how fast the tip of her shadow is moving, but will be just how fast the shadow is growing, okay? Relative to her, but she's moving. If we want the rate of change of the tip of the shadow, then what distance do we need? So, yeah, we need the tip of the shadow to something that's fixed, right? So the obvious thing is the light pole. So how fast her shadow is moving is the unknown, and that is dz dt. Does it make sense? So we don't, if they ask for how fast is the shadow length increasing, then we want dy dt. But we don't want that, so I'm going to even just take that off because that's not really involved. So we're just going to stick with x, how fast she's moving, and z, which is x, how fast her distance from the light pole is increasing, and then z, how fast the tip of her shadow is changing from the light pole. So that's our unknown. So then, step 2, what are the quantities? The quantities corresponding to these rates. We've already picked the symbols. What are they?
So this was step 1. Step 2, we have x is her distance from the light pole. I highly recommend that you write out what your variables mean. So when you get involved with lots of variables and lots of algebra, you know exactly what your variables are representing. And then z is length of the shadow. So it's the shadow, or the distance of the shadow tip from the pole. So, step 3. What is it we do in step 3? We start by, right, B, the equation that relates the quantities. So we want an equation that relates what two quantities? X and Z. X and Z. We need an equation that relates X and Z because our goal is, the centerpiece of this problem is the relationship that, the equation that relates dx and dz. Okay, so we've got triangles. We can use the Pythagorean theorem. No, that's not the way to go, because this is then that brings this into it, and that's a changing quantity, which we don't care about. So what else can we do that's simpler than the Pythagorean theorem that brings together x and z? So you have to recognize what you have here. As she moves away, think about, you've got some triangles. What's true about those triangles? So we've got a triangle here like this, right? And then we've got a larger triangle, in black, here. And what's true about those triangles? Yeah, they're proportional, they're similar, right? And as she walks, the similarity of those triangles will be maintained. Okay, so we could set up a ratio of z over 16 would be equal to what? So the ratio of the base of the big triangle to the height would be equal to what? So now what is this quantity right here? How much is that? Z minus x over her height, right? So we're doing the base over the height. So the base is z over 16, then the base is z minus x over her height 6. So you have all these kind of pre-calculus things that you have to have in your tool bag. So here's something new, similar triangles. So there's lots of geometry involved in these often. And if you need to go, and a particular problem, you need to go review, because you never picked up the tool along the way, figure out what you need to solve it. Okay, so then, what would we do? I think the hard part, this is the hard part to most of the problems, is this part. Getting all the symbols to match up with the given information and setting up the initial equation. That's 80% of the difficulty. So we're going to differentiate with respect to what? Z? Time. This is all about speed and feet per second. So when we differentiate with respect to time, it'll be dz dt, dx dt, that's what we said, right? That's what we needed. Okay, so I'm going to stop there. So based on what you did for today, that should be a breeze then. And then you got your known quantities. You can also use the similar triangles then to solve for anything that any value that you need at the current, where she's 35. So then the current value of x, after you do this, that current value of x is 35. Figure out what z is from the similar triangles. If you need it, I don't think you need it here. You're just going to end up with dx and dz. dx dt and dz dt. You're not going to have any x's or z's when you're done. Okay, anybody have a question? So hopefully this process and approach is now kind of coming together now that you've worked on it and we did another example. Anybody have a question? So I'm not going to finish it. Again, the goal was dz dt, how fast the tip of the shadow was moving relative to something fixed, right? So we need it all the way to the light pole. Last chance, questions? Okay, so let's move on. And my beautiful kids. Okay. So I have this. Let's go to 2. So what I'm showing here is. I'm showing, so f is some accumulation function, and r is the rate of change of that accumulation function, and n is the current value of x. So our n slider is the current value of x, and I'm showing a command line there for r of n, or the current value of the rate at the current value of x, okay? And so as n slides, it shows, with this black bar on the x-axis, it's showing the current value of x. So here it's showing the current value of x increasing from -4 to -2.5, and then it's going to start over. Okay, so we're focusing on this part, the interval of x from -4 to -2.5, and according to some accumulation function, this is its rate of change. So as x changes, you're seeing the rate of change change. And so I want you to, we're going to go through each of these 4 sections of the graph, starting with -4 to -2.5. And I want you to tell me, what is the rate of change doing in that section of the graph, and what can you conclude about the accumulation function? Okay? So we're really going to work on coordinating graphs, coordinating rate of change and accumulation in terms of creating the graph and really seeing the relationship between those two. So just talk for 30 seconds. In this interval, what's the rate of change doing? And then as a result, what can you conclude about the accumulation? Go. Okay, so in this interval, as x increases from -4 to -2.5, what can you say about the rate of change? What are you observing about the rate of change? Someone said decreasing. Would you agree with that? Is it decreasing for the whole interval? Yes. Okay, and what else can you say about the rate of change? It's always positive. Okay, so if it's decreasing and positive, can we kind of put that together and say that Rx gets less positive through this whole interval? Do you agree with that? It gets less positive. Meaning it's positive, and so in other words, it is decreasing. Is it fair? Okay. What does that mean for the accumulation function?
Always growing just instead of decreasing rate.
Okay, he said it's always growing. So he's saying that the accumulation is increasing through this whole interval. That whatever quantity we have, its amount is going up. And that's because Rx is positive. And the fact that it's getting less positive means that that rate, it's increasing the whole way. The accumulation is increasing the whole way. It's just increasing at a slower rate. We've seen that before. Okay, so I'm going to turn on the next. We'll turn on the next, what is that? From negative 2.5 to negative 1. Here we go. And let you go again. Okay, go for it. So now we're in the next interval from negative 2.5 to negative 1. Observe the rate of change, and let's make some conclusions about what's going on in this interval. Go. Okay, so you should have found this. So certainly when it's getting less positive, the rate is decreasing. What about then after it changes to negative and starts getting more negative? Is the rate increasing or decreasing? The values get more and more negative. Are those values decreasing or increasing? Decreasing. So this is continually decreasing from positive values through negative values, but decreasing the whole way. Okay, what about the rate of change? Or sorry, what about the accumulation function? So does the rate of or does the accumulation increase or does it decrease? She wants increase and then it decreases. Yeah, when the rate is positive, our accumulation is going up. When the rate becomes negative, then we have a negative change in y for a change in x, right? That's right, because rate of change, if it's negative, then our change in y, delta y, would be negative for a positive change in x. Because what? Delta y equals k delta x. So if you have a negative rate of change, you're going to get a negative delta y. Your accumulation is going down. So this is going to start increasing. Start at first increases. But then, that's when the rate is positive. And then it's going to decreases. It's going to decrease. And that's when the rate is less than 0. Are we good? Let's put a line here. Next segment. What is that? Negative 1 to 0.5. Here we go. So yeah, watch from the beginning. This is toward the end now. Okay, it'll start right now. What's the rate doing? Quick. It's getting louder, not softer. So practice using these phrases. Less positive, more positive, less negative, more negative. Those are the phrases we want to practice. Okay. What does it do first? So it does two different things. First starts with more negative. Then more negative, and then less negative. That's what you should have seen. It's always negative. So, is the rate decreasing or increasing?
Decreasing.
It starts, that would be decreasing. Numbers to get more negative are decreasing sequence, and then it will turn and start increasing. So this is decreasing, then increasing the rate. What does it mean for our accumulation? Decreasing the whole way? She wants decreasing the whole way. Agree? What determines whether the accumulation is increasing or decreasing? Just negative or positive? It's always negative. The K is always negative. K is always negative. So delta Y will always be negative. Okay? And that's going to be our negative rate of change. So this is always decreasing through here. Decreases. Okay, last part. Uh, 0.5 to 2. Okay, here we go. 0.5 to 2. Okay, how does it start? It starts by getting less negatives. Picking up from before here, it's still getting less negative. And then, when it crosses over 0, then it's getting more positive. Oh, I didn't leave room. So therefore, what's happening to the rate of change? Increasing or decreasing? Increasing. Increasing or decreasing? It increases through this whole, it's getting less negative and then more positive. That's increasing the whole way. Increasing the whole way. Therefore, accumulation. Well, just the fact that, see, look, here, this is important. Just the fact that the rate increases the whole way doesn't mean that that the accumulation increases or does something the whole way, right? What happens at first? Yeah, if that rate of change is negative, it's going to start by decreasing. And then, when the rate turns positive, the accumulation is going to increase. Okay, so hopefully this is making solid sense because it can get really confusing really quick. Okay, the next thing we're going to do. So let's talk about this, what the function looks like. So the accumulation function, in this first section, we said that the rate is getting less positive and the accumulation is increasing. Can you draw it with your finger? Draw it with your finger. What will that look like? Accumulation is increasing, but the rate is decreasing. Something like that. Okay, what happens in the second section? Increasing, but then, so it's getting less, the rate gets less positive. That means that it's still increasing at still increasing and the rate is decreasing, but then there's a moment where that rate is 0. So what happens to the accumulation at that moment when the rate is 0? Yeah, for a moment. So we call it like, so if you think of the y value as the accumulating quantity, it's kind of like that, it pauses, right? So for a moment, that value of the accumulating quantity pauses. That's how we're going to say it. And then after it pauses, then what will happen? Then it's going to decrease. Okay? Something like that. And then, in the next section, so what happens? Our rate gets more negative. So through this whole section, we know the accumulation is decreasing. But first it's decreasing at, it's going to decrease more and more. But then at some point, it's going to decrease what? So the rate of change will be increasing, getting less negative, right? Getting less negative. And then finally, it's going to decrease at first. Hit a pause at the bottom when the rate, so somewhere in there the rate was 0. Sometime in there the rate was 0. So the accumulation pauses, and then the rate becomes more positive, and the accumulation increases, and its rate of change is increasing. So we're going to stay away from these phrases. Increasing at a decreasing rate, decrease at an increasing rate. Let's talk about each thing separately. I think it'll make things less confusing. Talk about what is the accumulation function doing? Is it increasing or is it decreasing? And then, what is the rate of change? How is the rate changing? Is the rate increasing or is the rate of change decreasing? Especially when the accumulation is decreasing, trying to put those together in the same phrase becomes very confusing very fast. So I recommend keeping those things separate in separate statements, okay? Okay, so what do we not know about this accumulation function? Did I just draw an accurate representation of the accumulation function? Yeah, so this whole thing could be at 500, or it could be down at negative 1,000, right? So all we have is the rate of change, which gives us the shape of it, but doesn't tell us, we don't have one value of accumulation, actual value. So this really could be anywhere. It could be in negative territory, it could be where I've drawn it, it could be in positive territory. So let's just turn it on and see just that it's the same in shape. Come on. So how do we do? So in terms of the shape, we got the shape right, okay? Okay, so now we have to make sure, anybody have a question on this? Because the next thing we do can start getting really confusing if you don't have this down solid. So let's we'll look at that same graph. Okay, so here's the same graph. Now I got some questions for you. Okay, so I'm going to set it going. So this is the same one we just analyzed. And so the red tangent line is a kind of a visual of the rate of change at the current value of x. Okay? So if you're thinking about how the rate of change is changing, and you're thinking about how the slope of that line is changing. Okay, so where is the accumulation between -4 and 2? First question is, where is the accumulation decreasing, and how can you determine that in 2 different ways? Go, talk about that.
The whole interval from -4 to 2. In the whole interval, from -4 all the way to 2, where is the accumulation decreasing? Okay.
So you should have said from about -1.8 to about 1.1 or 1.1. Is that what you said?
Two ways you can tell that. What's one of the ways you could tell that the accumulation is decreasing from about -1.8 to about +1.1? What's one way you can tell that the accumulation is decreasing? Yeah.
The rate on the side shows a negative rate.
The rate of change is negative. If your accumulation is, if your function is decreasing, here, so this is, everyone listen, because this is, you got to have this down, or else the next part's going to be confusing. If the function is decreasing, then the rate of change is negative. How else can you tell that the function or the accumulation function here is decreasing?
The shape of the graph.
Well, what's the shape of the graph?
Well, it's
Going down, right? So the quantity, the y quantity of this graph is going down. It's going down, okay? But again, if the function is decreasing, that means the rate of change is negative. If the function is increasing, the rate of change is
Positive. Okay. Now, we want to talk about the rate of change decreasing. That can mean one of two things. There's two different ways that we've talked about earlier in class that the rate of change could be decreasing. The rate of change is becoming what or what if the rate of change is decreasing? I'm hearing some people say it. Someone in the back. The rate of change is becoming less positive or more negative. All right. Next question. Try it again here. Sorry. So we're talking about Rx is decreasing. Maybe. Let's do this. There we go. So here's the test. If Rx is decreasing, what can you say about the rate of change of Rx?
If Rx is decreasing, then what about the rate of change of Rx? What's that?
yeah, I guess so.
So just think of Rx as just a function. Forget about the fact that it's a rate of change of something else. It's just a new function. If that function is decreasing, then its rate is?
I'm not hearing enough people say it. Negative. So you all,
Having your little conversations about things other than math and thinking it's so easy. Right. So if a function is decreasing, then the rate is negative. And that's true about a rate of change function too. If the rate of change is
decreasing, then its rate of change, if Rx is decreasing, then its rate of change is negative. Okay, so here's the key. What can we say about the graph of f? So now we've got the rate of change is decreasing. The rate is becoming less positive or more negative. So what about the graph of f? Where is this happening? Where is the rate where is the rate decreasing? So first of all, find the interval where the rate of change is decreasing. Go. Find interval.
So in this case, we're saying it's less positive. Because we can look at that as less positive.
No, I'm talking about the rate of change.
Yeah. If we said we have the rate of change that's operating, so I mean less negative, it's still positive. So it's another.
First question first.
Yeah, that's I guess that's what I'm asking.
No it. Can't say it. Too many things going on. Okay.
The rate of change is decreasing. How would I find less negative on positive, right? We can say the graphic has negative positive, right? If we have a negative graph where it's less positive or
I wish we'll talk about it later, but I wish you would have focused on this question. Okay, sorry. Okay, so where is the rate decreasing? Where's the rate decreasing? From what to what? I'll do it in red. Someone said starting at -4. Do you agree? Up until when is the rate decreasing? Is it decreasing here? Is the rate decreasing here? The rate? Nope. The rate's getting, what we said before, less negative, which means the rate is increasing. So where does it stop decreasing? Right about here. So this is where the rate is decreasing. It's either getting less positive. Watch the line. The rate, watch the line. The rate's getting less positive. And when after it goes to the top, the rate is still decreasing because the rate is getting more negative. Till about where I've put the mark. And now the rate starts getting less negative. So it's now the rate's increasing. And here the rate is increasing. Okay. The rate of change is decreasing. Here's the key right here. If the rate is getting less positive or more negative. That's how things decrease. They're either getting less positive or more negative. So look at the red line. That's showing you the rate of change. Here, right now, it's getting less positive. And right now, it's getting more negative. So the rate is decreasing through that whole thing because it's getting less positive and then more negative. And what can we say about the accumulation then in that interval? So what's always true about the accumulation for that whole interval from -4 to about -0.5? Well, part of the way the accumulation increases, part of the way it decreases. So we can't say anything about that. Okay? What can we say about the shape of the curve? No. But something's got to be true the whole time when the rate of change is decreasing. What's that? Okay, yeah, kind of like, yeah. So basically what's always happening there is the graph is like turning clockwise. You see that? It's turning clockwise. So so you see this whole way through here, it's turning clockwise. Right at that point, then what happens? It starts turning counterclockwise. Graph turns clockwise. And what we get is what's called concave Down. Like a... No, it rhymes with down. Okay.
The rate of change is decreasing. It does not tell us if the accumulation is increasing or decreasing, because you got both, right? You got both. You got increasing accumulation, you got decreasing accumulation. So that's not what it tells us. But what it does tell us is that the graph from left to right turns clockwise or is concave down, like up round.
I'm here to help you. Whatever works.
Okay. So then, starting here, the rate of change is now starting now. The rate of change is doing what? Getting less negative and then more positive.
So the graph, I should say accumulation graph. Accumulation graph. So what does the accumulation graph do? Turns counterclockwise. Concave up. Like a cup. Okay, Cerny has an announcement. Listen carefully.